Testing, testing, testing. All right, good.
That's my job.
All right, thanks. So I've been at Fresno State for 22, 23 years. My research, I got my undergrad at MIT, my PhD at University of Virginia. I had a lecturer position at Virginia Commonwealth University, and then I've been happily ensconced at Fresno State for, like I said, the past 22, 23 years. And I'm a theoretical physicist that works on gravitational physics and also high energy particle physics type stuff. Okay, so welcome. Thanks for coming to my talk. Oh, and I should share my screen. That's the first thing I need to do. Okay, so I'm assuming you guys can see my screen. So the title of my talk is Gravitational Waves. It'll be a little bit, some historical stuff, and also I'll tell you a little bit at a non-technical level about some of the details of gravitational waves. At any point in the talk, if you want to stop and ask questions, please feel free to do so. So, and here's a cartoon picture of two black holes spiraling in, and those waves that you see going out are gravitational waves from the vent. Okay, the plan of the talk is I'm going to do some sort of early history of gravitational waves. Then I'm going to talk about what are called Weber bars and the Hertz-Taylor pulsar, which are two early indications or claims for detection of gravitational waves, although we'll find out the Weber bar claims not so much. Then I'll turn to a modern view of gravitational waves, and I'll describe again at some sort of basic level sort of the modern view of gravitational waves. Then I'll talk about the very exciting and relatively recent, scientifically speaking, LIGO direct detection. So these are actually the direct detection of gravitational waves, as opposed to something like the Hertz-Taylor pulsar, which is indirect. And then I will make a few final comments. Okay, so early history. So the first person to propose gravitational waves was actually not Einstein, but it was Henri Poincare. And he proposed gravitational waves in 1905 based on sort of an analogy with electromagnetism. So electromagnetism is an inverse squared force law, or electrostatics is, and so is gravity. So it makes sense. So it's reasonable to think that, you know, you have electromagnetic waves, so you should have gravitational waves. It's not exactly a very, there are differences between the two, as we'll see. But anyway, so historically, Henri Poincare was the first one to propose gravitational waves based on this analogy with E and M. Now, it was actually Albert Einstein, after completing his theory of general relativity, our best current modern understanding of gravitational effects. After completing his theory of general relativity, very shortly afterwards, he wrote a paper predicting gravitational waves, which were ripples in space and time. So my one slide introduction to general relativity. So you may have seen this cartoon picture that essentially in general relativity, Einstein saw gravity as a curving of space and time due to matter and energy. So in other words, if you place some large mass like the Earth in space-time, it warps it, it bends it, and then other things like this small moon basically will then move in a straight line in this space-time, and that is then seen as gravity. So basically, John Wheeler put it this way, gravity is geometry, and basically the geometry is determined by the things that are influenced by gravity. So Wheeler said it a little bit more elegantly, but that's essentially the idea that basically, well, so he actually said, matter tells space-time how to curve, and space-time tells matter how to move, okay? So a warning, this picture right here is grossly inadequate to really get at the details of what general relativity does, because what this is, this warping of this sort of trampoline surface, it's sort of an embedding of a surface in a higher dimensional space-time. So that's really not what goes on in general relativity. The space-time that's being warped is not, as far as we know, embedded into anything else. And it's not just space that's being warped as in this picture, but it's time as well. So it's basically space-time that's being warped, not just space as in this picture. So, but this is the sort of cartoon picture that people draw of general relativity. Okay, so then after his success in formulating general relativity in 1915, Einstein very quickly found not one, but 3 approximate wave solutions. And so this is my cartoon picture here of one of those wave solutions. This fellow Eddington, right, who actually was a big proponent of general relativity and was responsible for one of the first experiments to verify general relativity via the bending of starlight, Eddington actually criticized these solutions. He actually looked at them and he found that 2 of the solutions were spurious. They were non-physical. In other words, you could move to a frame of reference where there was no wave, there was nothing waving, and so they were basically mathematical solutions, but they weren't physical waves. Now, the third solution that Eddington didn't succeed in punching a hole into basically did seem to be a genuine wave solution, but there were differences between this wave solution and, say, other wave solutions, and in particular from electromagnetic waves. So, so what were the differences? So gravitational waves occur at higher order, okay? And what that means is they only occur at quadrupole order. So now, so in other words, the lowest order gravitational wave comes from a changing quadrupole. This is different than E&M. E&M, if you have a changing dipole, so if you have a positive charge and a negative charge, and they're time changing, that will actually generate an electromagnetic wave. That won't do it for gravitational waves. Basically, you have to have a time changing quadrupole. They're also actually monopole waves, not in E&M. So in E&M, there's no such thing as a monopole wave. So in other words, what would I mean by a monopole wave? Say you had a shell of charge and you puffed it up and then let it collapse, puffed it up and let it collapse. Well, that's a moving electric charge, but it will create no electromagnetic wave. You need a dipole for that. Now, there is actually a monopole, there are monopole waves, they're sound waves, and one example of that is like a frog. So a frog, basically, that's what they do. They puff out their throat and then pull it back in, puff it out, and that basically makes sound waves. And so there are such things as monopole sources for waves, just not electromagnetic waves. And similarly, there are sources for gravitational waves, but they occur due to changing quadrupole, not changing dipoles. The other difference is gravitational waves are super weak. They're extremely weak, and that's because basically the gravitational interaction is just very much weaker than the electromagnetic interaction. So so for example, if you take a proton and an antiproton and you set them 1 meter apart, basically the gravitational attraction between them is going to be 10 to the 40 or 10 to the 41 times weaker than the electromagnetic interaction between the two. So gravity is just inherently weak. So it's weak, and the lowest order radiation occurs at the quadrupole. And so for these 2 reasons, gravitational waves are very weak and therefore very hard to detect. Now, there's still some similarities. Gravitational waves still travel at the speed of light, and they're actually transverse. So in other words, the gravitational wave will travel in one direction, but all the action or all the changes are happening in a direction transverse to the direction in which it's traveling. That's actually very similar to an electromagnetic wave. Electromagnetic wave travels in one direction, and the electromagnetic fields oscillate in a direction perpendicular to that. Okay, so then time passes. The Nazis take over Germany. Einstein, very smartly, decides Princeton is a better place to hang out than Berlin, and he hightails it to Princeton, and then he starts working with Nathan Rosen. And in the meantime, Einstein had changed his mind about gravitational waves, so he actually agreed with Eddington, no, there aren't gravitational waves. So he and Nathan Rosen wrote a paper basically saying, no gravitational waves. Basically, you can always move to a coordinate frame where they don't exist, and therefore they're not real. So Einstein sent his paper to the Physical Review, which is basically the top journal. It still is one of the top journals. And okay, published my paper. So but now Physical Review, actually, they did what all journals do. They sent it to a referee. The referee was actually H.P. Robertson of Robertson-Walker Cosmological Solution fame, a professor at Caltech, and he didn't reject the paper. So that's, you know, so the thing is, usually you get a referee report and the referee says reject or accept. Robertson actually said, well, I have some questions. And there were 10 pages of questions. This was a 10-page referee report. Most scientific papers aren't even 10 pages long. So here's a piece of advice for the young scientists. If you get a 10-page referee report, that referee put in some serious time. You should pay attention to what they said. And again, Robertson did not reject, okay? But Einstein, he was upset. So this is his reply that I find very funny. So in 1936, dear sir, we, Mr. Rose and I, have sent you our manuscript for publication and had not authorized you to show it to a specialist before it is printed. I see no reason to address the, in any case, erroneous comments of your anonymous expert. On the basis of this incident, I prefer to publish the paper elsewhere. Respectively, Einstein, P.S. Mr. Rosen has left for the Soviet Union and has authorized me to represent him on this matter. So, okay, that's how Einstein was going to play it. That's not actually very good. That's not how you respond to scientific criticism. But no, Einstein, actually, next slide, you'll see Einstein recovered. So Einstein then, as Einstein said in his letter, Nathan Rosen actually went to the Soviet Union, and Einstein started working with Leopold Infeld, and that's a picture of Infeld up here, of Infeld, okay? So Infeld started talking with Robertson, and Robertson basically told Infeld the problems that he had with the paper of Einstein and Rosen, and so Infeld goes back to Einstein and goes like, hey, look, this Robertson guy is really on to something. And so basically they were working and working and working, and eventually they came back to the original thing. No, actually, Einstein was correct originally. There really are gravitational waves, okay? So, and basically what Einstein said is, note, the second part of this article was considerably altered after the departure to Russia of Mr. Rosen, as we had misinterpreted the results of our formula. I want to thank my colleague, Professor Robertson, for their friendly help in clarifying the original error. I also thank Mr. Hoffman for his kind assistance in translation. So now actually, Infeld talked with Robertson, and so Infeld knew Robertson was the referee, but Einstein didn't. So Einstein might have still been a little bit cheesed at Robertson, but at this point, all he knew is Robertson had given them good advice. They had changed their view, and now it was like gravitational waves are on again. But based on back of the envelope kind of calculations they'd done, Einstein was like, okay, sure, they exist. You're never going to see these things. And you'll see why. Well, one of the reasons is they're super weak, right? And so based on back of the envelope calculations, says Einstein said, fine, great, they exist, but you'll never see them. And so that's what this picture is. So this is Einstein looking at basically some fantasy thing of giraffes. So yeah, you'll never see a bunch of giraffes in space. You'll never see gravitational waves. Okay, moving forward from sort of ancient history to more modern times, in 1957, there was the famous Chapel Hill Conference on Gravity was organized basically to sort of start people really seriously thinking about gravity and how to detect gravitational waves, okay? And so here's a picture of the Chapel Hill campus. This actually was sponsored by the fellow called Roger Babson, who made a mint. I think he came up with some type of office supply that basically is super useful, and basically became a multimillionaire. Now, he used that money to fund what's called the Gravity Research Foundation. And this foundation actually funded the conference, and it funds other like really legitimate scientific endeavors. Like every year they have an essay contest, which I myself have entered. And basically the winners of the essay contest are usually like Nobel laureates, like Stephen Hawking, Penrose, that level of a person. So anyway, Gravity Research Foundation at that level is pretty serious. But Babson's motivation for founding this Gravity Research Foundation thing actually is a little bit sad. So when he was a child, he was sledding with his sister. His sister's sled went out on the middle of a lake, fell through the ice, she drowned. And so Babson, I don't know what the steps were to lead him to this. He was like, well, if gravity wasn't around, my sister would not have drowned. Okay. And so basically he founded this Gravity Research Foundation to come up with some kind of way to discover anti-gravity. Right. Now, as far as we know, that's not a thing, but the money that Babson used to found the Gravity Research Foundation is actually real. So anyway, he used it to fund this conference, and this was a watershed event. Like, many people came here, and in particular, this fellow, Joseph Weber, came here, and his takeaway from this meeting, Joseph Weber, was, by gum, we should make an effort to try to detect gravitational waves. And he went back to the University of Maryland, where he was working, and he started building the first gravitational wave detector, which I'll talk about on the next slide. There's one more like sort of historical story that I have to tell about this conference that it'll be funny for people who've had general relativity. So Feynman was also invited to this conference, and so he came late because he was busy, and so he arrived like a day or two late, and it was like a week-long conference. And now in Chapel Hill, it's in North Carolina, there are actually two other universities in the research triangle. So there's Chapel Hill, there's NC State, and there's Duke, all good research universities. And so Feynman flies into the airport in Raleigh, Durham, and he's like, oh, I don't know what university this thing is at. So Feynman is a smart guy. He goes to the nearest taxi cab driver, and he's like, hey, buddy, so yesterday or 2 days ago, were there a bunch of people in bad suits with bad haircuts, wearing glasses, looking in the air and going, G mu nu, G mu nu, G mu nu? And the taxi driver's, yeah, I know those guys. He's like, okay, where did they go to? Chapel Hill. Take me to Chapel Hill. So if you've ever had general relativity, the metric tensor and the Einstein tensor are both given G, and they have tensor index mu and nu. And so basically, if you hear people talking about general relativity, that's a lot of what you'll hear. G mu nu, G mu nu, G mu nu. So Feynman figured out how to figure out where the conference was by that. Okay, so Weber bar. So Weber bar, the idea is fairly simple. So you have a large mass in the shape of a bar, you suspend it, low temperature, and then you connect a lot of piezoelectrics to it so that it can sense small vibrations. Now, a gravitational wave comes in. As the gravitational wave passes through the bar, what it'll do, it'll stretch and squeeze the bar, and it'll make the bar ring like a bell, and so you can actually pick up the vibrations of the bar. Now, you have to do things, you have to have a low temperature, you have to suspend it, you have to isolate it from all other kind of noise. But in principle, this kind of thing would work. And so Weber, in the early 60s, he basically built and designed such a thing. And so here's Weber actually putting one of these things together. And actually in 1969, he apparently detected a gravitational wave. And so he published this. And so right away, a bunch of other people rushed to build detectors, even of higher sensitivity than Weber's, and to sort of confirm, because that's, I mean, a key thing. When you make a discovery, then you need sort of confirmation and so forth. Unfortunately, no one was able to ever confirm this signal. So, and it's now thought that basically what Weber saw was just noise. But okay, so, but the point is, he sort of kick-started this idea, or got people to thinking about, hey, we can really try to detect gravitational waves. Okay, so after the Weber bar thing, two astronomers, astrophysicists, Russell Allen Holtz and Joseph Houghton Taylor at UMass Amherst, they actually started observing a binary pulsar. So a pulsar is a neutron star that basically sends off radio and other waves along a certain axis like this. And it was orbiting another neutron star, and they noticed that the orbit was decaying. And then what their proposal was that basically the reason the orbit was decaying was it was losing energy, and the mechanism for losing energy was basically it was losing energy to gravitational waves. And so they could use general relativity to predict how much energy loss would occur. And so this was their explanation. And it was the correct explanation, as I'll show on the next slide. And this is Holtz and Taylor, after they've been told they won the Nobel Prize, having a great time. Okay, so again, here's the cartoon picture. So here's Earth. Here are two neutron stars. One is a pulsar that sends radio waves at the Earth. And the two neutron stars are orbiting each other, right? So this beam right here is just so that observers on Earth can get a handle on the orbital period of this binary neutron star system. Now, according to general relativity, this thing should be bleeding energy due to the emission of gravitational waves. And you can actually calculate what the power loss is. Actually, here's the formula for the power loss. So M1 and M2 are the masses of the two neutron stars. R is the distance, center to center distance between the two neutron stars. And then you can use this power loss to basically derive a change of radius as a function of time formula. So again, all from general relativity. And from that, you can figure out how much does the orbit decay as a function of time. Okay. And here is the prediction. So the line is the prediction from general relativity. The dots right here, you might think they're basically put on there. These are actually data points. And basically the data is so accurate. There are error bars on this, but they're so small you can't see. And notice that bang on, all of these data points fall exactly on the curve predicted by pure general relativity. So, okay, at that point, people were like, yeah, I mean, that's got to be gravitational waves. And so Holtz and Taylor won the 1993 Nobel Prize for the indirect detection of gravitational waves. Okay, so now moving on to the modern view of gravitational waves. So again, to summarize a bit, Einstein at first thought there are gravitational waves. Then Eddington gave him a bit of a hard time. And then working with Nathan Rosen, he was like, no, gravitational waves are just an artifact of the coordinate system that you use. And then after getting that 10-page referee report and thinking about it for a while, he said, okay, well, there are gravitational waves, but probably you're never going to see them. Now, basically, one of the things that convinced people gravitational waves were really real and detectable was basically the Feynman. And Feynman came up with this argument at the Chapel Hill conference that I discussed earlier. So Feynman had what's called the sticky bead argument. Okay, and this was to show that the gravitational wave solutions of general relativity did actually carry energy. So the sticky bead argument is actually fairly simple. You have a rod and you have two beads, these rings right here. A gravitational wave comes along, and basically using general relativity, you can find that the rings will slide over the rod, right? And again, they're a little bit sticky, so there's some friction. So basically, they're going to heat the rod. So and this is all just using general relativity. And so obviously, you make the calculation, the rings move, there's some friction, so some energy goes into heating the rod. So where does the energy come from? Well, the energy has to be carried by gravitational waves, either that or something's wrong with energy conservation. And so this was one of the things that convinced people, sort of theoretically, that gravitational waves should be real and they should carry energy, and actually they should travel at the speed of light. Okay, so we already talked about this a little bit, but gravitational waves, to have a gravitational wave, you need to have a time varying quadrupole mass distribution. So if you have a shell of mass and you puff it out and you let it shrink, that's not going to generate gravitational waves. What you need is a time varying quadrupole, like, for example, two inspiraling black holes or two inspiraling neutron stars. So if you look at that system, that has a time varying quadrupole, and that will emit gravitational radiation. Okay. Gravitational radiation is it's incredibly weak. So if you think of trying to detect it via a Weber bar, basically as the gravitational wave passes through the bar, it'll stretch the bar by some amount. And so then you can say, well, how much would it stretch it by? Well, in a bar that's 3 to 4 kilometers long, for typical gravitational wave sources, that stretching would be like 10 to the minus 18 meters. That's small. That's 3 orders of magnitude smaller than the size of the nucleus. So that's what this is why Einstein was sort of negative on the ability to detect gravitational waves. So what you're trying to do is you're trying to see a change in length over 3 or 4 kilometers that's basically 1,000 times smaller than the atom of a nucleus. That's hard. Okay, you can do it with interferometers. Okay, and that's what we're going to get to next. The final sort of thing I want to mention is that gravitational waves have 2 polarizations called the plus and the cross. And the polarizations are given here. And so let me remind you first of electromagnetic waves also have polarization, but those polarizations, so you can think of, well, the electric field oscillates this way or oscillates 90 degrees to that. And then anything else can be made of combinations of those two. So because gravity is, okay, so this is a little bit jargon, but because gravity is mediated by a spin 2 graviton versus electromagnetism, which is mediated by a spin 1 photon, because of that, the polarization of gravitational waves are 45 degrees to one another. And so what I mean by that is this. So take this top line here, and you have a ring of mass. So you have a ring of masses. As the gravitational wave passes through it, what's going to happen is that ring is going to get distorted. First, it's going to get squeezed into an ellipse this way, and then this way. And then as the wave goes through that ring, it'll keep doing that. Okay, that's called the plus. That's called the plus polarization, because basically if you take this figure and this figure and sort of draw a line through the axes of the ellipse, you get a plus. Now the other polarization is called the cross, because if you take that same ring, you let a wave go through it, what happens is, for the cross polarization, that ring gets distorted this way, and then this way, and then this way. And then if you draw a line through the ellipse this way and superimpose them on each other, you get a cross. Okay. And again, they have 2 polarizations, just like E and M, but the orientation relative, the orientation is different. So the 2 polarizations are shifted 45 degrees relative to each other rather than 90 degrees relative to each other. Okay, so now coming up to more modern times. So again, Weber claimed initial detection with his Weber bar. No one was able to reproduce it. Holtz and Taylor found really good indirect evidence that there were gravitational waves, but physicists actually wanted to see things as directly as possible. So in the mid 70s, so after Holtz and Taylor's announcement, these 3 fellows, so Drever, Kip Thorne, and Ray Weiss, they started talking with each other, and they said, you know what? The way to go about detecting very small changes in distance is using an interferometer. So, and I'll describe what an interferometer is in more detail on the next page, but it's basically using interference of different light rays with each other. And so anyway, these 3 gentlemen thought of using interferometers to detect gravitational waves, and their ideas eventually evolved into LIGO, which is the Laser Interferometry Gravitational Wave Observatory. And in the US, there are 2 of these sites. There's one in Livingston, which is in the swamp in Louisiana, and there's one in Hanford, Washington, which is in the desert of Washington. So if you look at these are very large experimental devices, and so they had to go where land is cheap, a swamp and a desert. Okay, and these are basically several kilometers long. I think like each arm of the interferometer is 3 or 4 kilometers long. Okay. So, and here's the basic idea that Drever, Thorne, and Weiss came up with. So you have a beam of light, and then basically you pass it through a system of mirrors that are perpendicular to each other. So one beam of light goes through here. There's a beam splitter here. This basically, they bounce the light back and forth to basically sort of effectively lengthen the interferometer arm. And then at this beam splitter here, the other half of the beam goes here, bounces back and forth between these mirrors. Then the light comes back, recombines. And if it recombines in phase, then what you'll get at this detector here, you'll get a bright spot. And if it comes crest to trough, you'll get a dark spot, and and anything in between. Okay, so that's the basic interferometer. So now let's take a sort of a side top view. If you have a gravitational wave that comes in from the top like this, okay, what's going to happen? It's going to stretch and squeeze the arm. So the arm lengths are going to change due to this passing gravitational wave. What that's going to do, that's going to change the interference pattern here at the detector. And you can in this way, you can measure very, very small changes in distance. You can measure those 10 to the minus 18 meter changes over the length of 3 to 4 kilometers. Okay, so but that's the basic idea: is set up an interferometer like this, wait for a gravitational wave to pass. The gravitational wave squeezes and stretches the arms of the interferometer, which then changes the interference pattern, and you should be able to see your gravitational wave. The big goblin, bugaboo, or whatever you have for this whole, or for this enterprise, is basically noise. So basically LIGO tries whatever they can do to get rid of noise. And so there's seismic noise. So this is a cartoon picture of the sort of noise budget for LIGO. So there's seismic noise, the fact that the ground is shaking. There's Newtonian noise, the fact that someone turned the fan on, that there's a wind blowing, that someone bumped a table. There's suspension thermal noise. So in this interferometer, you have these test masses with mirrors that are hung. And so basically the suspension system, there's thermal oscillations in that basically plays into the noise budget. There's the coating Brownian motion. So the mirrors and reflectors of this thing, they have coatings, and basically there's Brownian motion in the coatings that then contributes to the noise budget. There's quantum noise, and then you add all this together and you get this total noise budget that actually more or less follows the quantum. So the red is the quantum noise, but if you add all the other noise in, then you get this black line right here, okay? And this is more or less an accurate cartoon of what goes on with LIGO. And notice the sort of bucket, the bottom of the bucket for this thing is between 100 and 1,000 hertz. So that's the sweet spot for LIGO, okay? Now, this is the cartoon picture. This over here is the actual picture, and it's actually pretty close. That's pretty accurate. Now, there's these spikes in here that aren't here, right? And so I asked one time, I went to an experimental talk, and I said, what are those for? Because you see them in every LIGO plot where they give actual real data rather than a cartoon picture. So does anyone have a guess what those are, or want to make a guess? Okay, well, so they're called piano wire resonances, and so they're basically resonances from the essentially piano wire that's used to hang these test masses. So those have resonances, and that's what those are. So they're called piano wire resonances. Okay, anyway, so the sweet spot for LIGO is between 1,000 and 100 hertz. So that's where they're looking for their gravitational wave signal. And again, you have to have 2 detectors because, again, if you see something in one detector but you don't see it in the other, then you're suspicious that maybe what you're looking at is noise rather than a real detection. And in fact, now they have another detector in Italy called Virgo, and there's a detector called Indigo, which should come online in India, Kagra in Japan, and I think Australia is even thinking of a detector. Okay, so what can LIGO detect? And basically there's LIGO, and then A LIGO is advanced LIGO. So basically the sweet spot for LIGO is between 100 and 1,000 hertz. And so that's tuned to see neutron-neutron star mergers, black hole mergers, and neutron star black hole mergers. Okay, this picture up here kind of shows that. So basically, here's LIGO, here's Virgo, here's advanced LIGO, here's Kagra, that's the Japanese one, and they all have a similar noise bucket. And then you see down here, there's the things they can detect are supernova. Supernova also send out gravitational waves, actually a little bit higher frequency. Again, these LIGO, Virgo, et cetera, they can detect pulsars and then neutron stars, black hole mergers, that kind of thing. Those are the frequencies that they're looking at. There are other gravitational wave observatories planned called LISA and ELISA. So LISA stands for Laser Interferometry Space Antenna. So it's basically LIGO, but up in space. And if you look, their noise budget puts them here, okay? And that has a sweet spot at 10 to the minus 2 hertz, super low frequency. So there are events there that happen like this. So there are things like resolved galactic white dwarf binaries. So basically, instead of having neutron star mergers or black hole, you have white dwarfs that spiral into each other. Okay. Since the white dwarfs are less massive, the frequency is going to be much lower, right, than neutron star or black hole mergers. But white dwarfs are more common, so you expect to see these more common. Then there are other things like you have extreme mass ratio in spiral. So that's so what that means is you have like a massive black hole, like at the center of our galaxy, and then something like a white dwarf or an ordinary star falls into it. And that will also give off a signal, but again, at a much lower frequency. So basically, LISA is sort of complementary to LIGO in that actually it's, this is a mistake I had. I thought LISA would be higher in accuracy. It's not. Actually, notice the bucket doesn't go down as low. It's not as sensitive as LIGO, but it has a completely different frequency range that it's good at, okay? And and a lot of these you'll see ELISA, ELIGO. So basically these mean for evolving. So basically as time goes by, they upgrade the detectors, they make them better, and so that increases the range. So for example, this picture right here is an example of what happened with LIGO. So this is these white spots are galaxies, clusters of galaxies. And I don't know if you guys can see this, but there's this little purple region in here, which is huge astronomically speaking. But that was the reach of the initial LIGO. So that was what they could see, right? Then with advanced LIGO, which is actually, we're actually beyond this, but this advanced LIGO, look how much further it reaches. So, I mean, that's good because these merger events, neutron star, black hole merger events, they're rare. And so the more space you look at, the more chance there is of actually seeing one of these events. So basically, this is the difference between initial LIGO and then advanced LIGO. And as time goes by, they're improving the sensitivity. Again, the more space you can cover, the more chance you have of seeing stuff. So the actual first detection, September 14th, 2015, by a postdoc, Marco Drago. So the coolest postdoc name ever. So he's a postdoc at the Max Planck Institute in Hanover. And so he was actually there nursing the machines, and he was the first one to see evidence of gravitational waves. So this is the signal at Hanford. This is the signal at Livingston. And what you're seeing here is time and frequency. So what you're looking at, this is called the chirp. So as the black holes spiraled into each other, they basically go faster and faster and faster. And as they plunge finally into each other and merge, you have this sort of uptick in frequency. And so basically, you can see that basically the frequencies are like hundreds to then 256 hertz as they finally plunge into each other. And so again, this is kind of in LIGO's sweet spot, 100 to 1,000 hertz. And you have this chirp, which is the final sort of death spiral of these black holes as they merge into one another. Okay. And then the blue wavy line and the red wavy line and the blue wavy line down here, those are basically sort of the process signals where you can kind of make out, they're coming in, oscillating, then big oscillation, and then finally merge, and then they ring down. So this last end stage is like sort of the ring down as the newly formed merged black hole basically rings down to its final stage. Okay. So So here's more pictures of basically the same event, but this is the thing that like blew me away when I first read about this. So based on the analysis of this event, this first gravitational wave detection was the merger of a 36 solar mass black hole with a 29 solar mass black hole. And basically the final mass black hole that they got from this was 62 solar masses. So if you do the quick math, there's three solar masses missing between, adding these guys up and this final thing. So and you look at the time scale for this event, this is like fractions of a second. So what that's telling you is in fractions of a second, 3 solar masses worth of mass is being converted into energy, gravitational wave energy. So that's amazing to me. I mean, for the time when this was in operation, or when this was going on, this was the most powerful event in the entire universe, because you're converting 3 solar masses of stuff into gravitational wave energy. Our sun basically takes billions of years to burn through and convert not even a fraction of its mass to energy. So this is a powerful event. Now, since then, because of the upgrades, there have been about 10 detections, and they all have names like GW for gravitational wave, 15, 2015, 09, that's the month, 14, that's the day, okay? And so here's a sort of a graphical analysis of that. So basically what this shows, each of these dots right here, right, that's the initial black hole, and then the arrow goes into the final merged black hole. So basically these are the initial black holes and then the final merged black hole. And so there's a range of these things that they found. The two most interesting ones are the ones down here. So these are actually neutron stars. So these orange dots down here, they're neutron stars, and they merge and they become, well, this one we don't really know yet. Is it a black hole? Is it a neutron star? This one, I think that they're also still not sure. Is it a black hole or neutron star? But the interesting thing about these events is that basically they're neutron star mergers. Okay, and I'll say a little bit about why that's interesting. But of all the 10 that were events that were seen, it was only GW 170817 that was a neutron star merger, and we're pretty certain that GW 190425 was also a neutron star merger. Anyway, this is sort of a graphical summary of what we've seen. Okay, to the detection. Okay. So this is the first black hole merger. So this was the GW 170814. This was a black hole merger that was seen 3 days before the neutron star merger. And basically this was, I think, the first one where Virgo was also involved. And so basically this allowed much better localization on the sky. So basically if you have 2 detectors telling you where something is, well, if you have 3 detectors, you get a much more narrow patch of the sky telling you where to look, okay? And so again, these are the sort of chirp signals where you see this sort of uptick, and Virgo's not quite as good, or not quite as powerful, but you can definitely see there's a little bit of a chirp going on there, okay? And again, the point with 3 detectors and 4 and 5, more detectors you have, the better localization on the sky you can get. Okay, this is the really exciting one. This was GW 170817, again, 3 days after the previous merger that I talked about. And basically, they were able to, using the 3 detectors, they were able to say a very narrow patch of the sky where this event occurred, and it was a neutron star merger. And not only did they see gravitational waves, they saw gamma rays, they saw optical, they saw radio. And this is the event that led to the sort of statement, the birth of multi-messenger astronomy. We're seeing gravitational waves, gamma rays, optical, radio, and I think even, well, they should also see neutrino signals from these kind of things as well. Another thing, so this is actually the data from that. This is the chirp signal. So again, this is the neutron star merger. And so if you notice here, basically the Livingston, you can see the best. You can see the chirp here. Notice it's way longer. It's like several tens of seconds, okay? This is because the neutron stars being less massive than the black holes, basically the period over which this occurs is going to be much longer. The period of the chirp is much longer. And also you can see a much cleaner signal here, okay? And actually notice Virgo, you really can't see anything, but actually it was this lack of signal from Virgo that actually helped localize on the source, this source on the sky. The reason being is every detector has a blind spot, right? If you have the detector oriented like this and the gravitational wave comes like that, or at some angle thereof, basically it's not going to stretch the arms along the direction that would lead to a shifting of the interference pattern. And so what happened is Virgo saw a weak or essentially no signal. So they said, aha, well, the wave has to be in Virgo's blind spot. And then knowing what we know from the other two detectors, that gave a very narrow localization on the sky. And so they were able to point their telescopes there and they're like, wow, okay. And we also see like optical, radio and gamma ray stuff coming from there. That's really good. All right. So a few final comments. And actually, so by final comments, I really mean my own research on this. So, and also I want to take advantage of this talk to sort of, again, advertise my research and actually let students know that, that I'm interested in looking for research students. So I've worked on gravitational waves, and actually what, with a colleague of mine, Preston Jones, we recently published, well, not recently, 2019, so about 2 year ago, we published a review article of this idea we had. And the idea was, well, strong gravitational fields should be able to generate electromagnetic radiation. So this is very similar to Hawking radiation. Hawking radiation, well, for Hawking radiation, what you have is you have a black hole, strong gravitational field, and basically the black hole emits a thermal spectrum of electromagnetic radiation. Very weak, right? Very weak radiation, but electromagnetic radiation nonetheless. Now, however, gravitational wave background is very different than a black hole background. Black hole background is, to a rough first approximation, static, but obviously a gravitational wave background is dynamic, it's time changing. So why do we think that a gravitational wave background will emit or can create or can squeeze light out of the vacuum? And it's basically, well, it's basically because of this. If you look at the process from a Feynman diagram point of view, which I have written here, the pigtail curly lines are gravitons and the wavy lines are photons. And so the way you're supposed to read this diagram is from the bottom up. So what you have here, you have gravitons coming in and then you have photons coming out, okay? And so if you calculate the Feynman diagram things, you find out actually that process there, it occurs. The amplitude for this process to occur is non-zero, and now it's very small because again gravity is very weak. So the coupling where the graviton couples to the photon, that's very weak. So these are very rare. This is a very rare phenomena. But the point is, it's non-zero. Now, actually, Preston and I, when we did the calculation, we used something called Bogoliubov transformations and calculate the beta coefficient, okay, which is just buzzwords. But essentially what we do is we, in a gravitational wave background, we let a field go in and we let a field come out. And if there's more field coming out than going in, then we say basically the gravitational wave background has created something, right? And that's in fact what we find, and that's in accordance with sort of this Feynman diagram picture. Now, to give you a feeling for how small this is, basically, in our calculation, we calculated the relationship between the electromagnetic flux and the gravitational wave. This H plus, it's the amplitude of the gravitational wave, which is very small generally. And so if we put numbers into this, and another thing is our process works best for high frequency stuff. And so from the previous talk, black hole mergers aren't so great because they're actually low frequency. What we would look at is something like supernova, which can emit gravitational waves that are like 1,000 to 10,000 hertz, right? Even with that, the amplitudes, if you look at this, the amplitude is small. So you can see right away, the electromagnetic flux is going to be way smaller than the gravitational flux. But doing some back of the envelope calculations for sort of a typical supernova type thing, explosion, we get a gravitational wave flux that's of this order. And then using this formula, we get a small but detectable electromagnetic flux. The reason people haven't detected this is the frequency of electromagnetic radiation is super low. It's like 1,000 to 10,000 hertz. And we're not very good at detecting electromagnetic radiation in that low of a band. So that's one of the things we proposed in our thing is like, okay, even if our calculation isn't good, this is worth looking for. And by the way, there's other things that emit such low frequency electromagnetic radiation that would be useful to take a look at. So anyway, that's the end of my talk. So thanks very much. And I'll take questions now.
Hi, Doug. That was a wonderful talk. I appreciate your review of gravitational waves and also your sharing about your research. I was just curious, so does your research depend on the quantization of gravity in order to involve gravitons? And if so, does this mean that this effect would be brought into question if gravity cannot in fact be quantized?
No, so actually, if you take a look, these Feynman diagrams are all tree level. So, I mean, this, although the beta coefficients, the Bogoliubov coefficients are, well, let me say, so this is sort of the lowest approximation, the lowest order approximation that you can make. So, I mean, if, not seeing this, yeah, would be odd.
So I guess putting it another way, does the gravitational wave field come in as a classical field or a quantized field in this analysis?
Oh, yeah, it's a classical field. So basically, again, the calculation is very analogous to Hawking radiation. So basically, there you have a classical background, and basically you quantize the fields that play around in that background. And so, so it doesn't depend on the quantization. So it does not tell you if gravity is quantized or not. So it doesn't. So this is an interesting process, but not that interesting.
Oh, so it's kind of like quantum mechanics embedded in curved space-time ideas.
Exactly. So it's very similar to Hawking radiation. So in Hawking radiation, you assume a classical Schwarzschild background, but the fields that play in that background are quantized. So that's the same thing here.
So we shouldn't think that when we see graviton, that necessarily means quantized gravity. Is that right?
No.
Okay.
Right. So on that, so the last May, Frank Wilczek, Malik Parikh, and one of their grad students basically won the first prize for the Gravity Research Essay Foundation. So remember, I talked about Gravity Research Essay Foundation thing? Okay, well, they won it, and they actually won for some proposal that would actually prove the quantization of gravity. So they were basically proposing that they could pick out the noise in the LIGO detector, and that noise would tell you something, would tell you if gravity were quantized or not. So so there was a talk this Wednesday morning, and I think I sent out the link to some people here on that about that. But so Nathan, you've seen the paper on the archive, right? The Wilczek paper.
I don't think I've seen that paper. What is the title of it?
Oh, it's something like I'll send you, but something like the noise of gravitons or something like that. So the quantum noise of gravitons, and it's basically, if gravity is quantized, then the noise that they see in LIGO should somehow tell you that. But I went to the talk, right? And so I'm like excited, and then but at the end of the day, it's a very special kind of gravitational wave that they need in order for it to work. So it needs to be a squeezed state, and the guy who talked about it was the postdoc that worked with Wilczek, And he said, yeah, so for ordinary LIGO, you're probably not going to see this unless some special things happen. But he said, well, in cosmology, they do expect gravitational waves coming from cosmological sources to be squeezed. And so that would be a potential for seeing that. But for LIGO, he made some arguments why you might be able to see this sort of quantum noise effect, but he at the end he basically admitted, yeah, it's kind of a long shot for signals coming from LIGO.
Can I suggest, Doug, there is another possible source of gravitational waves from the Big Bang, which is the gravitational wave analog of the cosmic microwave background. And the idea is this, that if gravitational waves come into thermal equilibrium with the fireball at the very beginning of the universe, as we know for a fact that electromagnetic waves do, then there should be a definite ratio of power between gravitational wave background, let's call it the G and B, gravitational microwave background, and the well-known CMB, the cosmic microwave background, which is electromagnetic. And I think that might be a better evidence, if you like, for the quantization of gravitational waves, since it goes back to Planck, that if you see a turnover in the spectrum, that means the radiation is quantized, or at least that's my way of thinking about it. What do you think of the possibility of detecting microwave frequency gravitational waves as a way to detect whether gravitational waves are indeed quantized?
So, well, first, yeah. So, Ray, I think that one of the sources that they were looking at, Wilczek and his collaborators were looking at, were exactly those kind of things you talked about.
Oh,
Now, about
by the way, could you send me their paper? I'm also not familiar with it.
okay, so yeah, so it was the first prize winner in the GRF contest, and so they wrote an essay on it, and then I think they have a PRL version, and then they have a PRT version.
Oh,
Also something for the students. So also if you want to go start a rock band, if you have a hit, beat that thing into the ground.
I put in the chat box what I think might be the paper. Is it by Krauss and Wilczek, From B Modes to Quantum Gravity and Unification of Forces?
No, that's also an interesting paper, but yeah, that's not the paper. This paper it's like George Zarahid, Malik Parikh, and Frank Wilczek, and it's all within the last year. I'll send you guys the papers. So they're very interesting, but I mean, when you first read the abstract, you're like, oh wow, so they're going to be able to detect the quantum nature of gravity just using LIGO detections. Yeah, probably not. But I mean, what they propose is definitely feasible, just not exactly with LIGO, probably.
It's nice that they're using the noise of another experiment. It kind of reminds me one person's trash is another person's treasure, I guess, huh?
Exactly. So wait, Ray, you had another question, Ray? Or oh, you said something about microwaves. Yeah, so generally, one thing I learned from this research project is that most sources of gravitational waves are very low frequency stuff. So again, black hole mergers, neutron star mergers, they're in the 100 to 1,000 hertz range. Waves coming from supernova collapse, those are 1,000 to 10,000 hertz maybe. So, but finding gravitational wave sources that are like microwave frequency, yeah, I don't know.
yeah. Well, that brings up the difficulty. I mean, what we'll have to search for is a way to detect microwave frequency gravitational waves. That's a very tall order.
Well, and so let me just say also for the for just for the students, I mean, okay, why can't you have super high frequency gravitational waves? Well, you have to have a large amount of mass and you have to move it very fast. Well, large amount of mass means that you have a lot of inertia, so you can't move it fast. So basically, the things that you would do to try to have sort of a high frequency, signal or gravitational wave, they sort of work against each other. So to make a large gravitational wave, you need a lot of mass generally.
Well, the universe has a huge mass, and so when it exploded, there is a lot of mass moving very quickly. And
Yes.
so if you believe in thermodynamics, then there has to be, from just thermodynamic arguments alone, a thermal background for gravitational waves that is as strong as the cosmic microwave background, which we know is around 3 Kelvin. So that's a very powerful argument, a thermodynamic argument, that such gravitational waves at microwave frequencies where the Planck radiation curve turns around, in the microwave range, has to be there if we believe in thermodynamics.
I could also, I think, make a point about the large amount of mass moving fast. If I recall correctly, I think the quadrupole moment tensor in scales as the square of the mass, but the 6th power of the frequency. So I think that the high speed plays a more significant role than the large mass in the overall quadrupole. It's the 3rd time derivative of the square of the quadrupole. So that's why you get a mass squared, but then an omega to the 6th out of it.
Yeah.
Hey, I just had a question. I was just thinking about the problem of detection of this electromagnetic radiation coming from the GW waves. I was wondering if you could tell me what is the bandwidth we're talking about? What set of frequencies are we talking about? What are the issues with detection?
So I have to say, so I'm not an experimentalist, but let's go back to, let's go back and look at some of these. Let's look at something that's a little cleaner, maybe. Yeah. Okay. So if you look at these detections right here, so here's frequency and then here's time. So here's that chirp signal, right? Right. And so you can see it starts. So the signal starts like 50 hertz and then basically shoots up to 250. So that's the chirp signal. So that's the frequency range. And that's sort of the characteristic frequency that you'll get from these black hole mergers. And now let's go look at the neutron star signal. Okay, so here's the neutron star signal. Again, you have time and you have frequency. Notice, this also so for a longer period, but it also starts off low and doesn't really get up. It doesn't get up past like 500, right? In frequency range. So basically, for neutron star mergers or black hole mergers, they're all going to be sort of be between 100-ish and 1,000 hertz. So that's the frequency range that LIGO is working with. Now, the thing is, I had another slide. Let me go to that where so here. So if you look, again, this is pulsars, supernovas, neutron star, black hole mergers. So those frequency ranges all play around 100 to 1,000 hertz. Now, if you look at other things like white dwarfs, they're going to occur at a much lower frequency range. So this, I don't know if you guys can read this, but this is like white dwarf mergers. So those are much lower frequency ranges. So white dwarfs are much less massive than neutron stars and black holes. So the frequency that you get from those things is going to be much lower, right? Now, the advantage of the white dwarfs, though, is there's way more of them than there are neutron stars or black holes. So they're more common. Another possibility that you see up here, the low frequency range, is what are called extreme mass ratio inspiral. So what that means is one of these things is a giant black hole, like the black hole at the center of most galaxies, and then the thing falling into it is a small sort of solar mass black hole. So there's an extreme difference between the masses of the black holes, and so those kind of events lead to much lower frequencies. Okay, and again, with LIGO, you have no hope of seeing that kind of stuff, because notice the noise bucket here goes like this and then keeps going up. So basically LIGO is completely no good for seeing these things right here, for seeing these low frequency things. So that's what LISA and ELISA are supposed to do. So they're supposed to, you know, if they go up, you know, 2025, 2035, 2045, then they should be able to see some of these other like lower frequency events.
That's cool.
Doug, if I may ask about a slightly different topic in your talk, but I don't want to take us on a separate unless we're through with this.
Okay, well, let's see. So, do any of the students have questions or comments or? Okay, if not, go ahead, Nathan.
All right, thanks. So about Feynman's sticky bead argument, I've often been curious about it. I know it was used as a tool to convince, at least conceptually, why the detection of gravitational waves should be feasible or is real, at least, whether technologically feasible or not. I often wondered, though, was Feynman, in a sense, assuming that the response of the rod to the gravitational wave is different than the response of the beads? Because if the response is the same, and both the rod and the beads are oscillating together, you know, the stretching and compressing of space as a result of the gravitational wave, if they were to move together, you would not have any relative motion between them and hence no friction, which, if I remember correctly, was his argument for why energy would be delivered. It would, of course, be converted into thermal energy via the friction, right? So I'm personally, at this point, from my own personal study of this, convinced that materials respond differently. But was Feynman implying, just assuming really, that that's true between the rod and the beads, or in that model?
Right. So in the model, I mean, so the beads, well, and if you saw in the cartoon picture, the beads were assumed to slide across the rod due to the effect of the gravitational wave. And okay, so the rod has to also do something, but basically the motion of the rod was orders of magnitude smaller and therefore negligible compared to the beads. At least that's the point that Feynman had. And I mean, the thing is, given that we've detected, you know, that sort of the stretching and squeezing and dumping of energy into LIGO, like that's correct. Right?
Well, let me ask that. Did LIGO actually, was energy delivered to LIGO, or did LIGO just in a passive way demonstrate the existence of the gravitational wave, but not actually absorb any energy from it?
No, so I mean, so it has to have absorbed energy, right? Because basically the mirrors moved. You saw a signal, right? So I mean, there was a movement of the mirrors. That's why you get the interference pattern change.
So does that mean that the gravitational wave, after passing through LIGO, would have had less energy on the way out than when it came in?
Yeah, it's small. I mean, because all these things we're talking about are like tiny. So it's like, you know, we're changing the length of the thing like 10 to the minus 18 meters over a length of 3 to 4 kilometers. So I mean,
of course,
it's tiny, right? So I mean, for example, when I was getting ready for this talk, if you, just as a comparison, right, if you look at Jupiter and the sun, right, that's also a binary system, and that'll also emit gravitational radiation, right? How much gravitational radiation does it, what's the power? It's like 700 or 7,000 watts. Not a lot. So basically completely negligible for that system. Now, the Hulse-Taylor pulsar, in contrast, now I forget, but it was like 10 to the 22, 20 to 23 watts. So I mean, that's a power loss. That's, you know, but even still, I mean, compared to the total energy stored in the system, that's not a lot. I mean, so the decay is actually very, very slow. But I mean, and don't quote me on the whole stellar pulsar power thing, but it's like there's an order of magnitude difference between, say, the energy lost by the whole stellar pulsar versus like, say, Jupiter and the sun, right? Jupiter and the sun, I remember, was around 700 or 7,000 watts, and then the whole stellar pulsar is like way more. Okay, now now LIGO, the amount of energy that's delivered to the system due to the shaking because of the passing gravitational wave is going to be tiny, tiny, tiny. Now, but the thing is, like, let's say you place the same detector like an astronomical unit from that, right? Actually, I've heard say that, say, like, suppose you were one astronomical unit from merging black hole binary. Well, then actually the tidal forces of the passing gravitational waves, you would have no trouble actually seeing them, because as the wave passed you, it would take you and go like this, and then like that, and then like this, and you're like, aha, a gravitational wave is passing by and tearing me apart. So that energy to rip you apart is actually coming from the gravitational wave.
So I see. So Feynman really is assuming then in his model that different materials respond to gravitation in different ways as the wave passes by. Maybe like the intermolecular forces of the rod would make it more rigid in comparison to the free beads. I'm assuming he's treating them like free masses that would not have those intermolecular forces preventing them from moving.
Right. So I think all masses I mean, if the equivalence principle holds, all masses should respond the same in free fall to the gravitational force. But the particles that make up the rod, they have some other issues connected with them. Like you said, they're connected by intermolecular forces and so forth. So they're not undergoing just free fall. And the sticky bead, it had some very loose connection to the rod. So that basically, I guess it's then a question of difference in coupling. So basically the molecules that make up the rod are bound by hard molecular forces. The rod, the bead on the end of the rods were very loosely bound. And so they were the ones that would move.
Actually, Nathan, I can't place it right now, but Feynman made his arguments more concrete by pointing out that in the sticky bead argument, there is a fundamental difference between the rod and the bead, because the rod has a fundamental length scale, namely the Bohr radius, and therefore the rod could not respond in exactly the same way as the beads, and that difference is the reason why there has to be a differential motion between the rod and the beads, and that is at the heart of the sticky bead argument. I can't place but maybe Doug can do it. But he appealed to a scaling argument based on the atomic dimensions, specifically the Bohr radius.
Okay.
Basically, he's saying that there has to be a breakdown of the equivalence principle due to quantum mechanics, but he didn't put it in quite those terms.
Well, it just makes me wonder if you couldn't go a step further. And let's say, for instance, if you sprayed some charge on those rings, then you know that they would radiate electromagnetically when they move relative to the rod, for instance. And so now you have a transducer between GR waves and EM waves, right?
Yeah, I think that's right. But when Feynman made his argument, he just wanted to show in a thought experiment that energy must be transferred from the gravitational wave to matter, period. I mean, that was what he wasn't, thinking about conversion to from gravity waves to electromagnetic waves and so on. He wanted to answer certain objections that came up in the Chapel Hill conference, that maybe because of the equivalence principle, gravity waves don't exist at all because everything, free falls together and there's no relative motion. And Feynman came up with this sticky bead argument to counter those equivalence principle arguments. I think that there's a historical, I wish maybe Doug could point us to this. I think there's something like the notes of the Chapel Hill conference, the write-up. Do you have that?
So yeah, so I don't have that. No, but that would be interesting. Hey, so I don't mean to rush, but actually I just got a phone call. I'm supposed to talk to someone at like 4:15. So I mean, if there are more questions, comments, and Nathan, Ray, so I owe you guys the will check articles, which I'll send, but is there anything else?
Thank you very much, Doug.
Yeah, I was going to just say thank you. I'd like to read your article about GM waves producing EM waves. That'd be very interesting.
Okay, so I'll send that to you, Matthew, and then Nathan, Ray, I'm going to send you the articles by Wilczek and Company on graviton noise.
But I would also like to see
Thank you.
a paper on conversion to EM waves from gravity waves too.
Okay, so I'll send you that. So it's a review article from So
yeah. Okay, thank you very much for an excellent talk.
Okay, and our next colloquium I think is actually I think Nathan, I think you're the next one. So February 19th. So it's a little ways down the road, and I think and then Tori and Fred are going to give a talk. So, but anyway, so you'll be seeing from me the announcement for Nathan's talk February 19th. All right.
Bye.
Bye-bye.
Bye.
Thank you.
Bye.